Okay, yes, welcome back, welcome back. I have two things for you. I have the review for our exam, which is going to take place on Thursday. I wanted to ask a quick question, kind of off topic, but you never know what people are into. I'm trying to find somebody who knows how to write Android apps. By any chance, does anyone here know how to write Android apps?
What programs are you using it for?
Well,
Android apps, like apps like
an app for Android? Yeah. I don't know what your question back to me means.
I do Android apps like counting games.
Anyone who knows how to open up an app, an Android app of an open source one, open it up and know what the hell all that means.
Okay.
All right, maybe we can talk after class. All right, so that's the review for the test on Thursday. I also have the review for the final, which takes place next Thursday, right? Now this review that I'm going to hand out is a review that covers the entire semester, but I'm not quite sure our final is going to cover the entire semester. But I just want to give this to you now anyway, just in case, you know, at least you can start looking at the stuff toward the end, right? So I don't want you to feel like I didn't give you anything to get ready for the final, all right? I think as a class we need to discuss whether or not we want the final to be comprehensive or just covering stuff towards the end. What do y'all think? This towards the end? I thought some people might feel like the stuff towards the end was harder and they like the stuff in the beginning more. Why don't you take a look at the review I just handed out for the final, the one that says final exam review. Take a look at that and we'll talk about it next time, all right? Say, yeah, you know what, that stuff in the beginning, yeah, I feel good with that. You know, find the equation of a line. That sort of thing you're happy with. Domain problems, evaluating functions, sketching lines. Sound fair? All right, let's get on with today. What questions do I have for your homework? Or are there any questions on homework? Number 25. Let me turn my phone off. I'm pretty sure I left the ringer on here. Number 25. What page was that, sir? 432. 25. Is it this one, y equals 2 to the x plus 1 minus 3? Right there? Yes. Okay, so the instructions here are basically to graph this, right? Sketch this. So how do we sketch that? What type of function is it? Exponential, right? Because your x is up here in the exponent, it's an exponential function. How do we graph exponential functions? That's the other way. That's how we graph a log. We turn it into exponential. So how would I graph this? Crickets. Okay, so like a t-table type thing? Okay, so I'll make a t-table. But what am I going to use in the t-table? X and, do I use that whole thing? What's the base function, the toolbox function here? Just the 2 to the x. You don't need the plus 1. The plus 1 is going to tell me about shifting. The minus 3 is going to shift. So if I know what 2 to the x looks like, all I'm going to do with that is move it around after I graph it. Okay? Everyone understand you have to identify what the toolbox function is first. Now I make my table. What numbers do we always use over here? -3, -2, -1, 0, 1, 2, 3. All right, those are my numbers. And then plug those values in. 1/8, 1/4, 1/2, 1, 2, 4, 8. I'm not going to show that work because we've actually done that before, right? Now, do I need to flip these?
Yeah.
I'm trying to trick you. Do I flip those? No. If I was graphing a log function base 2, then I would. But I'm graphing an exponential, so I don't flip. So those are my points on my graph. Now, I haven't moved the function around, but let me go ahead and graph it first. I would go -3, and then 1/8, which is right there, -2, 1/4, -1, 1/2, 0, 1, actually, 0, 1, 1, 2, 2, 4, and then 3, 8. Guys, if I can hear you, everyone can, and it's a little bit distracting. Is that our final answer? No. Right, this is just the toolbox function. I have my horizontal asymptote here, right? Goes like this. And if you look at the review for exam 3, okay, this is very similar to what problem? Number 2. This is the same problem as number 2 on the review for exam 3, except instead of using 2, I put a 4 here, right? I put it in parentheses, which doesn't change anything. I put a 4 here, and instead of doing x plus 1 on the test, I put x minus 2, right? And I still use -3. So this is exactly like the problem you're going to get on the test. And this is exactly how you do it. So now I need to talk about the shifting. I'm going to take that graph. You always start next to the x. What does a +1 next to the x do? The one that's next to the x is left or right, correct? And it's always opposite of what you think, right? +1 would make you think that way, to the right one, but actually it's the opposite. So +1 is going to move me what? So that's going to move me left 1. And then what is the -3 outside by itself, right? It's not next to the x, it's down there, away. What does that do? Down 3. So what I have to do is I have to take every single point that I have and move it to the left 1, down 3. Left 1, down 3. Now, you can do this several ways. You can just start picking your points and moving them left 1, down 3, left 1, down 3. Or you can start with the vertical asymptote. Where does the vertical asymptote go? Left 1, down 3. So isn't the vertical asymptote more like this now? Right? Moving a left 1 doesn't really do anything because it's I said vertical. I meant to say horizontal, I'm sorry. Horizontal moves to the left and down. The left-right doesn't really matter. The up-down is what matters. So our graph, when we finish drawing it, should flatten out to that line. Does that make sense? Okay. So left 1, down 3 with every other point. This point right here, to left 1, down 3, 1, 2, 3 would put me really close to that vertical. This one, left 1, down 3, a little bit higher. This one, left 1, down 3, a little bit higher. This one's a little easier to do. Left 1, down 1, 2, 3 puts me here. You following what I'm doing?
Mhm.
This one right here, left 1, down 3, 1, 2, 3, that's this one. Left 1, down 3, 1, 2, 3 puts me here. And so what I'm going to do is redraw that exponential function. That last point I'm not even going to worry about. Flattens out, comes up like this. Doesn't have to be perfect. When I'm grading this, what am I looking for? I'm looking for the appropriate table, right? I'm looking for indication of what the shifting was. I'm looking for a movement of the horizontal asymptote properly, and then the graph.
So is it okay to just have one drawing?
Yes, one drawing is fine. Okay. Questions? Anything else on the homework?
I wanted to see in 462, number 91.
462. Remember what I said about your homework last time, right? That you need to get that together for Thursday? You're going to bring a homework folder or something that has all your homework in it? All right, don't forget about that. You said 91, correct?
Yeah.
All right, so number 91 is natural log x plus 7 plus natural log 9 equals 2. And we're asked to solve for x. All right, so solve each logarithmic or exponential equation for x. So is this a logarithmic equation or an exponential equation? Logarithmic or exponential? Logarithmic, because you have logs, right? The problem that we have, well, before I do that, when we solve log equations, we try and use the loop, right? But to use the loop, we have to have a log by itself, one log by itself. Right now, we have two logs on one side of the equation. So I try and condense the two logs down to a single log, which I can use property, I believe it was 6 from your notes. Someone can double check that. Property 6 says that you can take addition between two logs, right? Log base A, I think I used x times y equals log base A, x plus log base A y, right? That's property 6 from your notes. I'm using that property backwards, which means I'm reading it from right to left. I'm using this and turning it into this. So I'll take the two things in the logs, I'll multiply them. So I'm going to take x plus 7 and multiply it times 9. 9x plus 63 equals 2. Any questions? Got the two logs down to 1? Questions on that? Once you have this to one log, this equation with one log on one side, what do you do? What do you do when you have something like that? You're trying to get the x out of the log. Y'all okay? What happened? What happened this weekend?
It'd be like log base 2, e equals 9 plus
Log base 2. Yes. Well, hold on. Is this log base 2? It's log base e, right? That's log base e. But how does that help me? How am I gonna e to the second equals that? So you are you using that thing that I talked about in class, that loop thing? That's exactly what you're supposed to do at this point. Good. So to get the x out of the log, you have to get rid of the log. The only way to get rid of the log is to convert it from log form to exponential form. You do that by using the loop. You just have to know what the base is here. And the base here is not given to you, but we know the natural log of the base is actually e, right? That's e down there. Technically it's log base e, but I'll just write that. So I'm going to do that. That, right. And this was raised, right? Raised, not multiplied. And then this from here to here is the equals. So we're going to write down, my next line is going to say what? E raised to the second power equals 9x plus 63. So e squared is 9x plus 63. Now I no longer have my x trapped inside the log. My x is right here. This is a linear equation. I get on my calculator and I figure out what e squared is. Maybe I don't. You get on your calculator and you figure out what e squared is. What do you have? 7.3. Now, we have an issue here. I've told you pretty much to always round. 1 decimal point's good enough, right? That's what I've said. Okay, starting today, when we are doing these problems, let's start rounding a little bit more. Let's go a little further out, because if you want your answers to match the back of the book, you're going to want more decimals. And then we're going to be computing problems later that involve like interest rates and things like that. And you want to get as many decimals as possible so that your answer is as accurate as possible. So you got 7 point what on the calculator? 389? Okay, so let's say 389. Let's say that we can agree 4 decimal places. Let's go 4. Okay, so 7.389 what? 0 what? 0.5. So the calculator came back 0.5. If I'm going to go 1, 2, 3, 4 decimals, how do I round this 0? Up to 1. Why?
Because 5.
Because this is a 5 next to it, right? If it's 5, 6, 7, 8, or 9, we round it up. If it was 0, 1, 2, 3, or 4, we just leave it alone. So I'm going to use 7.3891. Okay? Now that's the left side of the equation. What's the right side? 9x plus 63. So now we just try and get x by itself. So how could I do that? Subtract 63 on both sides. So on your calculator you do 7.3891. Subtract 63. And you get negative 55.6109 equals 9x. Divide both sides by 9. $6.1789 is x. So if you on your test, if you don't round if you don't round it properly, you won't like lose all credit. But you want to round at least 4 decimal places. If you want to go further, that's fine with me.
Well, it was actually 6.1789, and then the next month was 8, so wouldn't it be 90? Let's say 90.
You could, yes,
I wouldn't be counted off.
you would not be counted off if you did that. That would be okay.
In the book, the answers show different.
So does it show -6 or?
It shows e squared.
Okay. E squared minus 63 over 9 or something like that?
Yeah, e squared minus 63 over 9.
Okay, so what they did, and I won't ask this of you on the test, but what they did is they left it in what's called exact form. So instead of trying to get on my calculator and figure out what e squared is, they just left it. So they brought the 63 over, so they said, okay, subtract 63 on both sides, right? And they said, then divide by 9. So they go e squared minus 63 divided by 9 is x. And this is what we call the exact answer. because there's no rounding involved. I mean, that is the answer. It's kind of like if I write down 1/3, do we all understand that that's 0.333 forever? So I can't write 3's forever. So we usually put a bar. But if you just rounded it to 0.333, this is not the same as this. So there's some error as soon as you round. I don't know if I'm making any sense at all. As soon as we round something like this, we've created error. Now, maybe error that doesn't matter, it's so small, but leaving it exact means that there is no rounding error. So I want the decimal answer on the test.
I was about to say, do you want that? Or just...
Yeah, no, decimal's fine. All right, we need to proceed, right? We have more stuff to do today. We've got some more equations to solve. All right, how about this? Solve log base 5 x plus log base 5 x minus 6 equals 1. I'll make this a little easier. Hold on. Make this minus 6, make it a minus 4. What do you think? You can put the logs together. Okay, you have two logs, right? The x you're trying to solve for is trapped in the logs, so we put them together into one log. Now, what is the operation going to be when I put those two together? Multiplication, right? Because I had addition. It's multiplying the x times this. So go ahead and multiply x times x minus 4, and what would you get? X squared minus 4x, wouldn't you? Like that? All right. Equals 1? The loop thing, right? So you're switching it. So the next line should be what? 5 to the first power, 5 to the 1, which is just 5, isn't it? Equals what? X squared minus 4x. And what? Huh? Well, hold on. Hold on. Yeah. Kind of, but kind of not. You're thinking the right way, but we would do GCF at this point if that was equal to 0. But it's not equal to 0. It's equal to 5. But what type of equation is this? Is it linear? It's quadratic, right? It's quadratic. It's a quadratic equation. So how do we solve quadratic equations? We move everything to one side of the equation. Everything to one side. So how can I get this 5 out of here? Subtract it. So I subtract 5. I subtract 5 over here. What's still there on the left side? 0. On the right side, x squared minus 4x minus 5, right? Can't put the 5 with anything, so I just throw it on the end. And now you can start talking about factoring the right side. Now you can do that. So we can either factor this using AC method with that little cross thing, right? What else could we use? Your other favorite thing that synthetic division, right? Grouping, Maybe, yeah. And what's the end-all thing we can use if we can't do, if none of those methods were to work? Quadratic formula. X equals negative b plus or minus square root b squared minus 4ac, all that stuff. Remember that? The point here is that this whole log equation at the end turned into a quadratic equation. So we should be able to solve a quadratic equation. Would you all agree with the statement that a college algebra student that successfully gets through college algebra should be able to solve a quadratic equation? That is safe. That's kind of like coming into this class, every student should have been able to solve 3x plus 1 equals 7, right? Everyone that walked in day one should have been able to solve that. Well, everyone day one leaving this class should be able to solve quadratic. Whatever method it is you're going to use, that should be able to be something you should do, right? So how am I going to do this? I'm going to factor it, AC method, because that's the way I designed it, so it would factor easily. It comes out to be x minus 5 times x plus 1. So there's a little kind of from here to here, it's like a question. You've got to ask yourself, can you get this broken down on your own? I set each of these equal to 0. What are my two solutions? 5 and negative 1. So I have two solutions. Now I'm going to put a little asterisk next to this for reason here. Check solutions. We are supposed to check our answers. Anytime you solve a logarithmic equation, you're supposed to check your answers because it could be that one of these answers doesn't work. In fact, let me look at the original problem. The original problem was natural log x plus natural log x minus 4 was equal to 1, right? Yes? If I take negative 1 and plug it in right here, someone on their calculator tell me what natural log of negative 1 is. Was log, oh, I'm sorry, it was log base 5. Okay, log base 5, log base 5. Thank you for pointing that out. Well, then I can't, it's not easy to plug in the calculator. Negative 1 though. What did I say about logs? What can you never plug into a log? A negative number or 0, right? So if I try and plug negative 1 in here, it won't work, will it? Which means that that answer is actually technically not an answer. Now, on your test, I just want these answers. I'm not going to require you to check them. All right? Just this. If you get to this, you get full credit. Yes?
If we only put the x equals 5, then
Well, as long as it is the only answer. There's a little bit of a thing here that's misleading. Students will think that if they see a negative, they throw it out automatically. But there are log equations that might look like this. Like, look at that. If I change this equation like that, and let's say one of our answers was negative 1, you would think, throw it out because it's negative, right? But if I put it right here and I square it first, it's not negative anymore. And if I put it here, negative 1 plus 4, that's 3. And that works. You see what I'm saying? So the answer here, whether or not it's positive or negative here, does not tell you if it works. It's what happens when it goes back in up here. So to be safe, I would just leave your two answers the way they are, or that way you don't have to worry about it. Now, the reason why I'm not having you check these answers is because nobody in here is building a bridge or an airplane today, right? So you always have to check your work if you're doing something where things like that are on the line, right? You want to make sure your answers are okay. Did you all ever hear about a few years ago? It was many years ago, I guess. That's the Earth. And then there's Mars out here. And we had, before we had landed there and sent the rovers around, we were first investigating Mars and just trying to figure out like what we could and couldn't do there. So we sent this probe out, and the probe went, and we lost contact with it. What wound up happening is we discovered that it just went, instead of going to Mars and going into orbit around Mars, which is what it was supposed to do, it just went right into Mars and impacted and blew up. And millions of dollars were lost. The reason why it happened was because there were engineers working on this project in Europe, and there was engineers in the United States working on the project, and they were, coding up the computer and everything to get this thing to go where they wanted to go. Well, the Europeans used the metric system, and U.S. uses the old British system, right? So you got feet and meters got screwed up in their computations, right? So the Europeans are saying, oh, it needs to be 1 meter, and the U.S. was thinking, oh, 1 foot, and that's a big difference, right? So they lost it. And it was a simple fix. All they had to do was double, maybe triple check their work to make sure it was okay. It wasn't done. We lost the probe. All right. Okay, so that log equation was an example of an equation, a log equation that turned out to be quadratic, right? It turned out to be a quadratic equation. Let's do a slight modification of that same exact problem. You know what, let's keep it 1. Keep it nice. What's the difference here? Subtraction. Everyone see the subtraction on this? That means we cannot use that property 6. We actually have to use property 7. Do I need to write it? No, you have it in your notes, right? Property 7. Subtraction between 2 logs turns into division inside of 1 log. So I write 1 log, base 5, and then I write a division. And then which one goes on top, which one goes on bottom? X goes on top, x minus 4 on bottom, and then what's on this side? Just the 1, right? So we've condensed the 2 logs to 1 using property 7. Now we come in with the loop, right? 5 to the first power is that junk inside. So 5 equals x over x minus 4. Is this a quadratic equation? No. Right? It's not a quadratic equation. This is a rational equation. So the way that we solve rational equations is we come in and we multiply both sides by the least common denominator, which in this case is what? X minus 4. So what I'll do is I'll multiply the right side by x minus 4. Whatever I do to the right side, I must do the left side. What happens on the right side? They cancel, which is why we did it, right? So that would go away. On the left side, I have to distribute the 5 through the blue parentheses. So when we distribute the 5 through, what do we get? 5x minus 20 equals, what's still over here? X. Okay, what type of equation is that? Linear. This is like what I said, every student walking in this class should have been able to solve a linear equation day 1, right? So now we've taken a logarithmic equation, we worked with it, it turned into a rational equation, we worked with it, it turned into a linear equation, and now we finally solve. You getting the idea here? These log equations eventually turn into something we can solve. So subtract x on both sides. Get 4x minus 20 equals 0. Add 20 to both sides. 4x is 20. So x is 5. Do we know if that works? We'd have to check it, okay? Which you don't have to do, but I'm just saying we can't just look at that and say, oh, it's positive, yes, it works. You would have to go back and check it in the problem. Any questions? All right, I want to look at something else we have not seen up to this point. I'll remind you of this, of something we did before. It's very similar to what I'm about to do. Recall that if I put something like this, 2 to the x plus 1 equals 2 to the 5, what did we say had to be true? If those two things are equal, then what has to be true? The x plus 1 up here has to be equal to the 5, right? Those have to be the same. So from that, all I did was just matched up the exponents. Those two had to be equal to each other for this to be an equality. Yes? The reason it worked is because they both had 2, right? So these match exactly. So whatever the powers are had to be the same. And then we solve that, we get 4, right? We have something very, very similar to that with logs. Okay, so the new thing today is that if I have log base, let's say, 2 of x plus 1 equals log base 2 of 5, notice where the equal sign is. It's between them, right? You have the same log on both sides, don't you? Same base, same base. So the insides, in order for these to be true, would you agree that this inside would have to be equal to this inside? Yeah? So all you have to do is set this one equal to this one, just like we did up there. Can you see the difference between the two? This one, the thing that's the same is that the base is both 2. Here, what's the same? The log is the same. So what's inside of them must be the same. Follow? So I would say x plus 1 equals 5, which means x is 4. So we actually have a property we can write down. What was the last property I gave you? 8? 8, right? So we will add one more property to our list of properties, property 9. It says that log base anything of x equals log base anything of y means what? What must be equal to what? If those are equal, then what must be equal to what? X must be equal to y. So if you have the same exact logs and they're equal to each other, then what was in the logs has to be equal to each other. All right, now let's see how we can use that for a particular problem. You're not going to like this one. Okay, natural log x minus 1 plus natural log x plus 3 equals natural log 3. Can we use the property I just gave you? Not yet, right? Not yet, because how many logs do we have on the left side? 2, and on the right side we have 1. To use the property, we have to have the same log on both sides, right? So I have 2 over here. I can't quite do that yet, but can I make those 2 1? Yes. I can put these 2 together using property 6, because there's addition between them. And when I do property 6, I'm going to multiply the 2 pieces together, aren't I? So I need to multiply this times this, don't I? Now this one takes a little more work. It's not as simple as just, oh, look and do it. You have to FOIL that, don't you? So I'll do that above this just so we can see it. I'm doing x minus 1 times x plus 3. And then I do x times x, which is x squared, right? And then minus 1x plus 3x, which is 2x, minus 3. Good. That's what you get when you FOIL that thing out. And then equals natural log 3. Yeah, now we have log on each side, right? Same log, and then what we do is we say, okay, if we have the same log on both sides, and we have equality between them, that means whatever's here has to be equal to whatever's here, right? Agreed? So that means that x squared plus 3x minus 3 must equal 3.
Plus 2x.
Yes, plus 2x. Thank you. What type of equation is that? Quadratic. We solve quadratics by getting everything to one side. So I'll subtract 3 on both sides, right? Subtract 3, we get x squared plus 2x minus 6 equals 0. Questions, comments, concerns, gripes? Praise? No? You praise the problem? Or no? Nothing good to say? How are we going to do that? Well, you have AC method, right? Grouping, you have synthetic division, all of which will fail. So the only thing left is the quadratic formula. It's the only thing left. So I'm going to go to quadratic formula, which remember is x equals negative b plus or minus square root b squared minus 4ac. When did we have to use this last? When were we using this most recently? Find x-intercepts of quadratic functions. So we had this on our previous test. We had to use that. So I identify what a, b, and c are. What's a for me here? B is, c is negative 6. Plug and chug. Negative b is negative 2 plus or minus, what's b squared? 4 minus 4 times a, which we said was 1, times c, which was negative 6, all over 2 times 1, so 2 times 1 is 2. That's just everything plugged in. So I sit there and I work that out. What's going to be left underneath that square root? It's under there still. This is 4, right? I have a negative times a positive times a negative. So all of that together will be a positive.
24.
So this is 24, and we're adding 4. So 28. So we'll have negative 2 plus or minus square root 28 over 2. And then you can grab your calculator and take the square root of 28. 5 point what? 5.29. Negative 2 plus or minus 5.29 all over 2. And now you do the plus and the minus. So what's negative 2 plus 5.29 and then divide by 2? So on your calculator, negative 2 plus 5.29, then after that divide by 2. 1.645? Okay, it's 1.645, good enough. 1.645, and then the other one?
Negative 4.645.
Negative 4, is that right? Is it? It's negative 7.29 divided by 2. That shouldn't be bigger than 4. Negative 3.645?
Yeah.
Double check the calculation on that for yourself and see. That all right? We don't have to check the answers, okay? We'll just say, you know, if The good news is that if there is an answer, if a solution exists, it's one of those. Could be that one of those is bad. Could be both of them are bad. But at least we have some candidates for answers. That's pretty much the extent of the logarithmic equations that I would give you on a test, that type. What I've done today, what I did last class. I'm not going to push it any further than that. Sound good? All right, now I want to go back and revisit exponential equations. We started out, when we were doing exponential and log equations, we started with exponential and then we went to log later. I'm coming back to exponential. I think I told you when we did exponential in the beginning, I said these are the basic ones and later on we'll do harder ones. The time has come for the harder ones, all right? So let's try something. I think what I'll do is I'll start with the basic one to remind you of how we did it and then we'll move on from there, okay? So let's do something like this. -4 plus 5 e to the x equals 14. So I'm trying to solve for x here. X is trapped in an exponent, right? Not in a log like the last problems, or the problems we've been doing most of today. I'm trying to figure out, get that x down. We talked last class about the only way to get an x down is to change it, change the form from exponential to log. So what we did before is we tried to isolate this term. So we first add the 4 to both sides. That gives us 5 e to the x is 18. Then what? Divide both sides by 5. E to the x is 18 over 5. Are we good up to that point? Both sides divided by 5. This is multiplication. Divide by 5. Divide by 5 goes away. You get e to the x, right? That doesn't look anything like a 5. 5. Now what? So you switch it to the other form, right? So what you're trying to do is switch it to this form where we use the loop, right? What we know is that when we do the loop on a log, we get this, right? So this raised to this should be equal to this. What's the base going to be? The same as the base here, right? E. And then what are we raising e to? The x, so this side should be x, right? And then what's this? It's equal to 18 over 5, right? So we have taken it from exponential form to logarithmic form. Do you all follow that? Now what is log base e? In reality, what is that to us, log base e? That's natural log, isn't it? So this really says natural log of 18/5 equals x. And so you get on your calculator, and all you have to do is figure out what natural log of 18 over 5 is. What is it? 1.2809. 1.2809, good enough, is x. What do y'all think about that? Do y'all remember that, doing something like that before? Okay, I'm going to do the same exact problem I just did, I'm going to do it a slightly modified way to show you what I think might be for some of you a little bit of an easier approach to the problem. All right? If you're happy with this, be happy. The problem with it was getting, I think the most challenging part of it, and tell me if I'm wrong, is going from here to here, right? Because you might mess something up there. So that's where I would like to start. Okay, so if I'm trying to solve this, e to the x equals 18 over 5. I'd like for you to look in your notes at property 8. Property 8 said log base a of, was it x to the n equals n log base a of x? Right, that was property 8. And the property said that if you had a power on something, right, you could always pull the power out if you had a log out here. If you have a log in front of something, you can always pull the power out. So right now, I have something to a power, right? I want you to see the exact match. I think I should put this underneath here so it's on camera. That's the property I'm using. What I have is something, right? Something to a power. To a power. Now I realize that this x is down here and that x is up there, but that's not the important thing. I have a base to a power to a power. Yes?
Yeah.
Okay, the property says that I can pull that power out, which means that x would come out, right? If I had a log in front, which I do not have a log in front, do I? So I'm going to make a log appear. And I can do that as long as I do it to both sides of the equation at one time. So I'd like to come out here in front of this one with the log so that I can apply the property. So the log I'm going to use can be any log I want. I'm going to use the natural log because that's the key that's on my calculator. So what I'll do is from this equation, I will take natural log on both sides of the equation. Okay, natural log on both sides. Now I have a log, that is a log, right? Natural log is a log, of something to a power. The power can now drop out in front, can't it? So I drop this power out in front on the next line. Oh, hold on. Y'all should have said something to me. This side should be what? That was complete brain fart on my. What's this side? 18 over 5. Okay, so I took the natural log on the left side, natural log on the right side. I dropped the power out front. Nothing has changed here, right? Anybody remember what natural log of E is? It's 1. Natural log of E is 1. We did that on our calculator, I believe, last class. Or it was a property, one of the properties. Natural log of E to 1 is 1. The point is that this is a 1, which means that we get x is what? Natural log of 18 fifths? Isn't that exactly what we were doing before? I mean, isn't that the same exact answer? It's just another method of solving these things. I'll give you another example of this method. This will be the last example of this method I give you. How about this one? What if I have 5 to the x minus 1 equals 3? Let's solve this. So the thing that I'm trying to get out of the exponent is the x, right? But there's a minus 1 next to it. So I've got to pull that whole thing down. Can I just drop it in front right now? I can't, right? I can only drop this thing in front if what was here? A log. So I'm going to come in with the log on both sides. The log I'm going to use, natural log, because it's my calculator key. So I'm going to go natural log of the left side and natural log of the right side. Now I can pull the entire x minus 1 out in front. When it comes out in front, it needs to be in parentheses because it's 2 terms, right? X minus 1 is 2 terms. Then I have natural log 5 equals natural log 3. What next? Natural log of 5 is not 1, right? Could I divide both sides of this equation right now by natural log 5? Could I do that? Would it go away over here? Yes? Over there, get on your calculator and do natural log of 3, divide that by natural log of 5, and tell me what you get. What do you get? 0.68. Anyone else get 0.68? 0.68. What's still on the left side? X minus 1. We have 0.68. Final step, add 1 to both sides. X is 1.68. Done. Does that way seem more confusing or easier?
Just kind of crazy that I just walk the log in there.
Well,
But, I mean.
with the equations, we were always able to like add something to both sides, right? Subtract both sides, multiply both sides by something. We're just taking log on both sides. That's all we're doing. So I'm doing log of left, log of right, and then working it out. How would this have been done using the old way? I would have to recognize this and fill in these pieces, right? So what would go here? 5. What would go here? X minus 1. What would go here? 3. Now what? Do you remember how to do this? Change a base formula. Change a base formula. Log base A of x equals natural log x over natural log A. Remember that formula? So it'd be, it would be natural log 3 divided by natural log 5. Holy shit, well that's what we had here, isn't it? Isn't it?
Yes.
And then the other side is x minus 1, the other side is x minus 1. So it's the exact same thing. It gets you to the same place. You just need, as a student, to pick which one you prefer. All right? Now you ready for the harder problem? I'm going to give you one of these and see how you do with it. If anyone passes out or throws up, then we'll stop. Now that's an exponential equation right there. That's got more teeth on it than just a normal old exponential equation. You're trying to solve for x. How is it that I told you to solve for x for an exponential equation before? What did we do? Tried to isolate it, right? We tried to isolate that, like in the previous problem, we tried to get e to the x by itself. Here, what's the problem with trying to isolate? There's 2 of them, right? We have a 3 to the 2x, and then I have also a 3 to the x. I have 2 exponential terms. Now, if these were logs, would I care too much? I could put them together, right? Because I have the properties of logs that I can condense things down. But with exponential, there's no property. Also, can I multiply this -10 times 3 and give me -30? What's the order of operations on things? Exponents before multiplication, right? So before I can multiply this, I would have to know what x is, wouldn't I? Because what if x was 2, then this would be a 9, right? Not a 3. So you cannot put those together yet. I'm just pointing that out. So what I need you to do right now is squint your eyes, do whatever you got to do and see if you see this. Is this the same thing? That is the same thing? Why? Because 3 to the x times, or 3 to the x to the second means you multiply these two. X times 2 is 2x. So that's the same thing? No one disagrees? Now, if you could, please, again, squint your eyes and tell me if you see this. If I say, look, let u be equal to 3 to the x. In other words, everywhere I see a 3 to the x, everywhere I see one, I'm going to replace it with u. Then what does this equation become? What's this? That's u, right? That's u? U what? U squared? Minus 10 times u, right? Plus 9 equals 0. Do you agree with that?
Yeah.
I've done something that we do a lot in math. I made what's called a substitution. I saw something that was common in both of these terms. I recognized that this looked quadratic, kind of, because I had something squared minus something in front of that thing, plus a constant equals 0. So this is kind of like, it was, it's like x squared, right? Ax squared plus bx plus c equals 0. Can you solve that equation up there? How could you break this down? Factor it, AC method, or the synthetic division? Just notice you have u's, not x's, right? So if you do this, minus 9 and minus 1 will work. U minus 9, U minus 1. And that gives you two solutions. They are what?
9 and 1.
9 and 1. We're not done. Do you see why we're not done? What was the original problem asking us to do? Solve this equation. The variable they gave us was what? X, right? And then we come back and we say what? U is 9 and U is 1. That's like me asking you what your favorite color is, and you're like, I don't know, Ford. You know, I mean, it just doesn't make any sense. I'm asking you what X is, you're telling me what U is. I don't care about what U is, I want to know what X is, right? So we got to finish and we got to go backwards. So just replace it. What's U? We said U was 3x, right? So you see this equation right here? Just rewrite it, replace U with 3x. 3 to the x, not 3x. 3 to the x is 9, right? Replace this one with 3 to the x is 1. What type of equations are these equations? Exponential, right? But they're nice, they're little ones, right? They're little mini exponential functions. How do we get the x out of here? How do we get it down from there? Come on, get down. How do we get that down? We can do log, right? We do log. Now you can either do that loop thing, or you can do what I just showed you where you take log on both sides. So my instinct just from looking at you, and trust me, this is not a good gauge because I'm not sure how close I am to this, but I think y'all like the way where y'all just rewrite the log, where you don't do log on both sides, where you just rewrite the log for this. How about for this one on the left? Log, fill in the blanks. What's the base? 3, what goes on this side? X, what's in here? 9. Okay, the other one, same thing, log, what's the base? 3. X, 1, Don't sound too enthused. All right, how about the left side, or the left equation? How do you do this? Maybe you just look at it and remember what it meant. This means 3 to what power is 9? 2. But if it's not something you can think of, you would go change a base formula. This is natural log 9 over natural log 3 is x, right? Do that on your calculator. You get 2. Or you might get something like 1.9999, or you might get 2.00001 or something close to 2. Yes, 2. Good enough. And then on this one, it's natural log 1 over natural log 3. Anyone remember what natural log of 1 is? What any log of 1 is, all the time, always? 0. 0. So if the top is 0, then the bottom doesn't matter, does it? This is 0. We have 2 solutions to that nice exponential equation. We'll put that on the test for a bonus question. Y'all like that? Y'all like bonus questions? There's something like that for a bonus. All right? And I haven't even started today's new material. It's depressing. This will officially be our last exponential equation. This will not be a bonus problem. This will be a problem like something on a test, all right? Anybody see an issue here? Trying to solve for x? Again, there's 2 of them, right? Could you use your loop here? Let's just try it and see what the hell happens. If I do a loop, fill in the blanks here, how would it look? What base here? Could I do the 8 also? It's one or the other, right? So let me try it with this. If that's 5 here, what am I raising the 5 to? The 3x minus 1. Did y'all see that? 5 to the 3x minus 1 must equal what? That whole thing, right? 8 to the 2x. Do y'all agree that that log does represent that? This converted from exponential form to log form is this. Yes? Okay. Now, let me just write that without all the little pretty boxes and stuff. This is log base 5, 8 to the 2x equals 3x minus 1. Now, this is the first time this has ever happened. Over here, instead of having log base 5, 8, we have 2x up here also. So we cannot use change of base formula there because of the 2x. Do y'all see that? However, property 8 will let me do what with that 2x? Pop it out front, right? See, here we have to use property 8. I still need to get this thing out of here. I can drop it out in front. Why can I drop it out in front? Because there's a log in front of it, right? There's a log sitting here. If the log's in front, that power can come out. So now I've got this. 2x log base 5 of 8 equals 3x minus 1. Are y'all still there? What now is log base 5 of 8 on your calculator? So how are you doing that on your calculator? You're doing what? Natural log 8 divided by natural log 5, which is 1. What is it? 1.292. So So 2x times 1.292 equals 3x minus 1. What type of equation is this? Linear, right? 3x minus 1 is linear. This right here, this is just 2x times this number. What's 2 times 1.292? About 2.6 or so? 2.58? Or what? Yeah, no. 3? What is it? 2.58? Okay. So this is about 2.58x equals 3x minus 1. Are you still following what I'm doing here? Yes? Now just get all your x's on one side and divide through, and you should be there. If I decide to just subtract 3x on both sides, if that's what I wanted to do, which I can, then this would give me negative 0.42x. Negative 0.42x equals negative 1. That's what will be left on the right side. And then I divide both sides by negative 0.42 and get my final answer. X is? What is it? 0.1? No, it should be bigger than 1. You're taking negative 1 and dividing by negative 0.42?
No, it is.
You do the other way?
Yeah.
Okay. So you have to do the 1 divided by, what is it?
Negative 2.38.
2.3. It'll be positive though, right? Because you're doing a negative divided by a negative? On your review for exam 3, it's very much like number 10. In fact, if you look at your review for exam 3, I've basically done problem like number 5, 6, 7, 8, 9, and 10. I've done all those today in class. Problems very similar to those. But I haven't talked about anything like 11, 12, and 13. So I think it is time that we move on, right? We beat the exponential and log equations enough. Break? 5-minute break? No, it's good and bad, right? We'll see what happens. All right, well, let's continue. There's a few problems here we still need to address that will be on our test on Thursday. I think you're going to find that what I'm about to do is more just like, here's a formula, let's apply it. There's not a whole lot of new technique to talk about, all right? So this is an application of some exponential and log equations. So 4.5 applications. This section is littered with things that you can do with logs and exponentials, but I'm only going to choose to do 2 types of applications: simple interest and carbon dating. Those are the only 2 applications that I'm going to show you. The book has plenty more. So the first application is simple interest. Now, simple interest works as follows. You go to the bank, you get a credit card, right? Maybe you do, maybe you don't. You ask for a credit card, they give you a credit card, they loan you money, right? They let you use their money, except that you have to pay it back at a certain interest rate. Yes? And so how much you owe is determined by that interest rate. And all of it can be written in a formula. We call it a simple interest formula. And there's 2 formulas that are generally used when it comes to computing interest. So I'm going to give you both of them. The first one is this formula, A equals P times 1 plus R over N raised to the N times T. That's the first formula we're going to use. I'll show you the second one after we talk about this one. Yes?
Is that an L or like an I?
Where?
Where the plus is?
This right here?
Yeah.
That's a 1.
Oh,
1, yep. And an R, yes. So let me discuss what each of these letters means in the formula. First, let's start with P. P, anyone know what the P is? Principal. Principal. Not you're going to get sent to the principal. The principal is the amount of money you start with. So, like if you go and you ask the bank to give you a loan, that's the principal is how much you ask for. Or if you go put money into a bank, into a savings or checking account or a CD or something like that, that's how much you start with. All right. So I'm just going to put next as principal starting amount. The next letter in our equation that we're going to talk about is R. Little r is the interest rate. And it must be written as a decimal. Don't mess this up on the test. Anytime you're talking about an interest rate, like if you go to the bank and you say, what's the interest rate? They tell you like 2% or 1.7% or something like that, right? You always have to take that and convert it to a decimal. And we'll make sure everyone understands how to do that once we do an example. All right, so that's your interest rate right there. That's your principal. The T is the time, and it's always measured in years. So like, you know, I'm borrowing $10,000 from the bank to go to school, student loan. I have a certain interest rate on that loan. I have a certain number of years that it's going to take me to pay it off, or a number of years that I'll be in school that it's going to be accumulating interest. That's T. So if it's 2 years, T is 2. 5 years, T is 5. 6 months, T is 0.5 or 1/2. Understand? So no matter what, you have to always be looking at time in years. All right, so the last letter here is N. And N is well, no, not lesser, when you do A also. N is the most complicated of all. This is the number of times interest is what they call compounded per year.
So is that like if we get interest every 6 months?
The bank determines how many times they want to calculate your interest. They can do it yearly. That means that once a year they compute the interest. They can do it monthly. They can do it quarterly. They can do it daily. It all depends on the bank themselves. So they have flexibility on how they want to use this N. All right, we'll look at different scenarios. And what we'll determine is that the N really doesn't make a huge difference. Not that big of a difference. What's important is that it's the number of times per year. So if I tell you that the bank computes it monthly, then what would N be? 12. If I say they do it yearly, N would be 1. Quarterly, 4. All right? So N is, in the wording of the problem, you'll be able to determine what N is. And the last thing in here that I have not accounted for is the A, right? The A is the amount in the account at end of the T years. let's look at it from the standpoint of you want to go save money, all right? Let's say you put in $10,000 into some account. They have an interest rate of 2%. You want to leave it in there for 5 years. They compound the interest monthly, so n is 12. Then if we plug everything into this and we compute that answer, that's how much would be in the account after that 5 years was up. How much money would be there? Okay, it would have grown, right? A little bit? Yeah? Okay. Now, you can see from this equation that if I know P, I know R, I know N, I know T, I can get A, right? But what if I only know A, I only know P, I only know R, and I only know N, and I don't know T? Then T is up here, isn't it? And T then would be, our variable would be an exponential equation, wouldn't it? So I'd want to solve for T, which means I'd have to use the methods that we developed in the previous section. So let's first do an example where we just compute what A is, and then we'll actually do a problem where we have to use what we did in class in the last section. Okay, here it is. Example. $20,000 is placed into an account at a rate 3.25%. That's never going to happen, but at least not nowadays. $20,000 is placed in an account at 3.25% for 3 years with interest compounded monthly. How much is in the account then after the 3 years? After 3 years, how much is there? This is assuming you didn't go in there and pull a bunch of it out and spend it on iPads. You just leave your money in there, let it build up. If you do what a different way? How are you going to do it? You mean just compute the interest separately and then add it to it? I guess if you get the right answer, but the formula that you're using, does it account for the monthly?
Yeah, because it's going to be 20,000 divided by 100 times 3.25. That's how much you get monthly. And times 12, 12 months.
Okay, why don't you try your answer and see if you get what we get. Try it and let's see if it matches. Yeah? Okay, so let's try this. What's A in the problem? What's A? Isn't that what we want to know? Okay, what's P in the problem? 20,000. What's R in the problem? Yes, R, we have to convert the 3.25% to a decimal, so you always move the decimal 2 places to the left from where it started. That's how you convert a percent to a decimal. What's time? 3. What's N? 12. Is there anything else I need? No. So this is it. So A should be equal to 20,000 times 1 plus 0.0325 over 12 raised to the 12 times 3. So all I'm going to do is get on my calculator and do this. Order of operations is important here. Do what's in the parentheses first. Do the division first. So on your calculator, take 0.0325 divided by 12. What do you get? You should get a pretty small number. So what I recommend is however many decimals your calculator goes out is how far you should go out. So someone tell me what they got there. And add 1 to it, because that's the next thing you do, right? Add 1. You get 1 point what?
Could we just
0, 0.
let that code copy right into the calculator?
Yeah, if you can, as long as you don't make a mistake on it, that's fine. 1.0 what?
27.
0027.
08333.
The further you go, the more accurate it's going to be. When you say put the whole thing in the calculator, you mean just type it in all at one time? Okay. Yeah. Now take this answer, 1.0027333, and raise it to the 36th power. And what do you get? 1.02266 164 161. Good enough. Take that answer, multiply it times 20,000. 22,000.
22,045.
45,045.
Yes.
Point
3232.
3232. I'll just go 32 because this is money, right? I'm only going to go to the nearest cent. Did you get the same thing? Okay, so I'm not sure what formula you're using, so I would be cautious. What's that? Yeah, just double check it. I can maybe talk about it later, like which one you're using, but were you even close to this? 20 what?
28,400.
Okay, that might have been the next formula we're going to use. That might have come from there, but we'll see. So your $20,000 sat in the bank for 3 years, and you gained $2,000 in that 3 years, right? But with inflation, it's more like now worth only $15,000, right? Any questions on the application? That's just plug and chug into the formula. Now, how about something like this? This is more like a test problem. You put money into account for 10 years. Wait, hold on. Account at, let's say, 12.3%. You found this really, really good investment that the average return is like 12%, like stock market type stuff. You put money into account at 12.3%. Interest is compounded quarterly. How long until you double your money? You might be sitting there thinking, I didn't give you enough information, right? Maybe. What do you have, for sure? Interest rate? What's our interest rate? 0.123. What else do you know? Interest is compounded quarterly. What variable is that?
4. Oh wait, that's the number.
That's the number. What letter is it for us in our problem?
And
N. Okay. That's all I gave you, right? So what things do you not know? The amount, A, what we started with, and T, right? Those are things I didn't give you. But what is it that I want to know?
how long until you go there?
How long, right? So which of these things do I want to know? I want to know what T is, right? How long? But I did say something about the money, right? I wanted to be able to double it, right? So if I start with P, right? If I start with P, whatever that is, $10 or $1 million, what do I want my A to be at the end? Double that, right? 2P. Do you agree? So I did kind of indirectly tell you what A was. It's double whatever P is. Now, let's just write the formula out, and you're going to see that the P is not going to matter. What's the formula? A equals P times 1 plus R over N to the NT, right? Let's start plugging things in. What was A? 2P, right? Twice what I put in. That equals what? P. I still don't know how much I put in. 1 plus what's R? 0.123. What's N? 4 raised to the N times T. 4T. What can you do? Does anyone see what you can do here? With the P's? Not subtract because it's multiplication. I can divide both sides by P, can't I? And the P completely goes away. So divide both sides by P. I divide here by P, I divide here by P. I just get 2 equals. I need someone to do this for me. What's 1 plus 0.123 divided by 4? Say it again, 1.03075. And now we need to raise that to what? 4T. Everyone understand? We did 0.123, divide by 4, add that to 1, we get this. I raise that to the 4T. Does everyone see that we're trying to solve for T? T is in an exponent. Yes? So how can I do this? I'll give you a hint. Turn it into a log, right? Yeah, let's do it. Let's see. How would this work? If I were to rewrite this as a log base something, something equals something, rewrite that exponential in log form. What's the base of this log? Careful. The base is the thing that's being raised to the power. So wouldn't our base be this weird thing, 1.03075? Isn't that our base?
Yes.
And then that's being raised, so this side is what over here? 4T, and then what's in here? 2. Everyone agree that that log matches up? Right? If I take this, raise it to the 4T, I get 2. That's this equation. The loop gives me this. That means that creates that log. What can you do on the left side of that log to do that on your calculator? What do you have to compute? Natural log of 2 divided by natural log of 1.03075, right? That equals 4T. So take natural log of 2 divided by natural log of 1.03075. 22.886. And then 22.886. And then divide that by 4 to get T. What is it? 5.72? And that ain't bad.
That's years.
That's years. I guess that's not bad.
Okay.
If I told you you could double your money in 5 or 6 years, yeah, but 12.3 ain't gonna happen. Not safely. That's not a safe investment. You don't, right? I mean, is it impossible to get 12% return on something? No, but it's risky. It's like gambling in Vegas, right? Could you win the $1 million? Yes. Could you lose all your money? Yes. Right, Vegas ain't built on winners. What do y'all think about that? Does it seem odd to you that it didn't matter how much money? Or does that seem reasonable? Like this means if I put $10 into this account, in almost 6 years I'll have $20. But if I put 100,000 in, I'd have 200,000 after 6 years. So it's the rate at which the time it takes to double the money does not matter. The amount of money you put in does not matter. Does not impact that time. What do you think?
Y'all look enthused.
Okay, let me give you the other formula. I'm afraid we're running out of time. I'm a little concerned right now. The other formula is this one. Now, I hate to say it, but this is the formula that most banks use. That's A equals P times e to the RT. Now, e is that natural base. Remember, we talked about the natural exponential? That e is the natural exponential base. What do you notice does not appear in this formula that was in the last one? N. Okay, so remember I was saying the bank could do the interest, yearly, monthly, quarterly, daily, right? This is the formula they use if they're computing the interest what they call continuously. That means that they're always computing the interest. If they do that, then this is the formula. So this is called continuously compounded interest. Now, it may sound to you like, whoa, I don't want my bank doing that. That's going to be, they're going to take all my money if they compute the interest all the time. But it turns out that this is the way to go because the answer does not differ too much from what we would have before with the other formula, but this formula is much easier to work with. Right? We don't have that 1 plus r over n. We don't have that thing in parentheses. It's just e, and we love e, don't we? We do. So let's do a problem using this formula. P is still the amount we put in, R is still the interest rate, P is still time. A is how much is left at the end. So what I'd like to do is the same exact problem we just did, the same one. We want to double our money, 12.3%. This time, I'm not going to tell you it's compounded monthly or anything. I'm just going to say it's compounded continuously. So how long to double money at 12.3% continuously compounded? If you look at your review for exam 3, problems 11 and 12, like look at 11. What interest rate would you need to turn $8,000 into $9,000 in 3 years if interest is compounded daily and continuously? Oh, by the way, scratch out daily on number 11. That problem is extremely difficult to do. So on number 11 is just continuously, right? On number 12, how long to double your money if it's compounded monthly and continuously? That's number 12 I'm talking about right now. So if you're doing number 12, the first one, monthly, which formula would you have to use? The one before this. And then continuously, use this one, right? You see the difference in the wording of the two? Okay, so what would our formula look like here? What's A going to be for us? 2p again. This side's going to be, for this particular problem, it's 2p equals p e to the, do we know the r? 0.123. And then t, right? What happens with those p's again? Cancel out. So 2 is equal to e to the 0.123 t. Can you rewrite this as a log? It's log base what? Log base e. Over here, what's on this side? 0.123t. What's on the inside over here? 2. But what is log base e of 2? What does that really mean? ln of 2, right? Do I have any questions on where I got that from? So this is really natural log of 2 equals 0.123t. Take the natural log of 2, and you get natural log of 2. What is it? 0.693. So 0.693 equals 0.123t, and now divide through by 0.123. 5.63? Now, what was it in the previous problem? It's like 5.7? It's close. It's not exactly, I mean, you might argue, you know, there's a difference between $5.6 million and $5.7 million. Yes, I agree. But that's the way banks do it. Sometimes it helps, sometimes it hurts, right? If you're saving money, it helps. If you owe money, it's a little bit, hurts you a little more, right? Questions? Do you see this is just an application solving an exponential equation? This is really the part of this that's from last section is this right here. That's it. What do you say, because it's 4 o'clock and we have half an hour? I give you the option. We can talk about reviewing for this right now. I can try and do as much as I can in the next 30 minutes. Or I can just do number 13s and show you the radio carbon dating. So we can throw out carbon dating if you don't want to see it. Or I can do it, but we'll have less time to review. So what do y'all think? Carbon dating or not? Throw out carbon dating?
Yeah. Will we be tested on carbon?
I won't test you on it. Okay. So where should we start with this review? Yeah, I mean, we did do a lot of them. That's why I was saying, do you want to see the carbon dating? You still don't want to see carbon dating?
That'd be a bonus question.
Well, you have one already. That one exponential I'm going to give you. Yes.
Are we going to have a cheat sheet?
Yes, you can have a cheat sheet like you normally can have, 1 page, front and back, no worked out problems. On the final 2, yes, on all tests, yes. Well, that's what I'm talking about right now. I can 30 minutes, I can do as much as I can. Huh? No?
I don't have any answers and seeing if I work it to work.
I like this doing it by myself and watching the video.
You want to go home, in other words. Okay, I tell you what, if you feel good, I will put together, see, I'm trying to think of how much time I actually am gonna have.
I'm just, can't we see the answers, so.
I might actually have the solutions to this already somewhere. 'Cause this is an old review. So I might be able to get these for you. Either way, I'll get you the answers. Can't promise you the video, but I'll promise you the answers. So what I'll say is,
Worked out answers or just?
worked out answers. Worked out answers. Let's get everyone signed in for credit today. Extra credit. Let's see. Do I ever start it over here? Where do I? Never started over. Started over here. So Simon, what I'll do is I will give you the opportunity. I'll give you the opportunity at this point to go home, or you can stay and I can answer questions if you want to go over any of these. All right? Okay? The sign-in sheet's going to go around. Here's what I do. Here's what I will do. I'm going to start doing a video for this right now. Okay? If you want to leave, you may. But I'm going to sit here and just work through these. So please, if you can, as you leave, just try and keep it down if you are going to leave. If you want to stay, you can. You're not going to hurt my feelings if you go. But I want to try and knock out as much of this as I can the next 25 minutes. Yes?
I thought yours there was going to be a Thursday.
Yes.
Do you want to see homework or just see when back?
When you're back, that's fine. All right. Number 1. Hey, why don't we do this when we come back on Thursday for the test? Do you want to take like the first 20 minutes of class to answer any questions? You want to do that? We'll say, so like the test will start at 2, right? But from 2 to 2:20, I'll answer any questions. 2:20 sharp, we start the test. If there are no questions, we start as soon as, you know.
How much time do we have for that?
Hour 15, hour 20. I have to make the test first to see how much. But remember, we are planning to talk and do more afterward. That's the plan. Never works out that way. Okay, find the inverse of a function. So what we do, and I apologize, I'm not going to turn around and ask you any questions. I'm just going to do this, all right? I will say what I'm doing, but I'm not going to. Okay, so the first step was to replace f of x with y. And then the second step was to switch the x and y variables. And then the third step was to solve for y. Now this was tricky because we had a rational equation over here, and so I have to multiply both sides by y plus 5, or y minus 5. 2y plus 1, y minus 5. I know that's off camera. It's got to be. So I'm multiplying both sides by y minus 5 to get it to cancel. On the left side, I distribute my x through. I get xy minus 5x equals 2y plus 1. And now I'm trying to get y by itself, so I have y's here, I have y's here. I get both those y terms on one side of the equation. Everything that doesn't have y on the other side. So I'm going to move the 2y to the left side by subtracting it. So this came over, and then this negative 5x can go to the right side, become positive 5x plus 1. Once I do that, I've got two terms with y. I factor a y out. And then finally, at this point, I can get y by itself by dividing both sides by x minus 2. So x minus 2 here, x minus 2 here, cancels, y equals 5x plus 1 times x minus 2. Oh, and that equals that inverse of x. Thank you. The second problem on the review asks you to graph the function f of x equals 4 to the x minus 2 minus 3. So to do this, I realize I'm trying to graph an exponential function. The base function or toolbox function I'm trying to graph is 4 to the x. So I start with a t-table, x, 4 to the x, and then I'm just going to shift it around. I plug in my standard numbers, -3, -2, -1, 0, 1, 2, 3. Those get plugged in. 4 to the -3 is 1 over 4 cubed, which is 1/64. And then this one's 1/16. This is 1/4. Plugging in 0, I get 1. Plugging in 1, I get 4. Plugging in 2, I get 16. Plugging in 3, I get 64. So those are my numbers. That's going to give me a rough idea of what this graph looks like. So I'm going to move to the left 3 and up 1/64. So it's going to be very, very small. -3 up 1/64, just barely. -2 up 1/16, just a little bit more. -1, I come up 1/4. And then at 0, I'm at 1. At 1, I go all the way up to 4. And then at 2, I'm at 16. I'm going to be off my graph already, so I'm just going to draw this and just let that take off like that. And then remember, I have my vertical asymptote off to the left, horizontal asymptote. I said that twice already. All right, so I have my horizontal asymptote out here to the left. So now that's not my final answer. I need to move this thing around. So the -2 up here, opposite of what I think. So it's going to go right 2 and then down 3. So I move every point to the right 2, down 3. When I say down 3, this vertical, horizontal, geez, it just wants to be vertical. The horizontal asymptote is going to come to the right 2 and down 3. So my new horizontal is going to be down here like this. And then just take every point and move it. And this is just kind of eyeball it. To the right 2, down 3, 1, 2, 3. It's like here. This one to the right 2, down 3, here. Right 2, down 3. There, and right 2, down 3, here. So it's that same picture taking off real fast. It's just been translated to the right 2 and down 3. All right, so for the next problem, graphing log base 4 of x. I should have probably put graph f of x equals log base 4 of x. I left off the functional notation, but I think everyone kind of gets what you're supposed to do there. What I need to do to graph a log function is actually graph the exponential function for that base. Or not graph it, to get the points. So to do this problem, I'm actually going to make a table using 4 to the x, because that's the base. Well, what do you know? I did that in problem 2, didn't I? So I don't even have to do this work. All I have to do is take these points and do what with them? Flip them. So instead of graphing the point, let's see, this first one, instead of doing -3, 1/64th, I do 1/64th is my x coordinate, -3 is my y. Then the next point would be 1/16th and -2. The next one is 1/4, -1. Next one is 1, 0. And then I just do that for all the points and I graph it. So my new graph, or my log graph, is 1/64 to the right and down 3. So right there, then 1/16 to the right, down 2, then 1/4 to the right, down 1, then 1 to the right, and I don't go anywhere. And I can keep doing this and graph all of them, but you get the log that looks like this. And this time I have a horizontal asymptote. That's vertical. That one's vertical. Vertical asymptote.
So number 3 is just the same thing as number 2, just swap.
That's right. But it's the number 2 before you moved it. Because we did this to do number 2, right?
Yeah.
But then we moved those points around. Because it's log base 4x, all I need is this table. Make it the same. It's never happened another way. I've always used the same base in problems 2 and 3, so that it's not double the work, right? So all you really need to know for number 3, problem 3, is that you need to swap the points from problem 2. You'd be amazed at some of the things I get, though. People are trying too hard sometimes. All right, number 4. So number 4, solve this equation. 2 plus 4 natural log 3x plus 4 equals 4. I'm trying to isolate the log so that I can use my loop. So first thing I do is subtract 2 on both sides. When I subtract 2 on both sides, I get 2 on the right. Now I need to divide both sides by 4 because that's multiplication. When I divide the right side by 4, I get 1/2 or 0.5. And now that I have a single log equals a number, I can come in and do my loop. Remembering that the base of the natural log is actually e, so my e to this power should be equal to that. So I have e to the 0.5 equals 3x plus 4. .64, did anyone get e to the 0.5? We just check. I haven't used it. 1.6. 1.648. Yeah, okay, good enough. 48 equals 3x plus 4. Okay, I'm going to say dot, dot, dot. Is that good enough? I've gotten into a linear equation. Just move things around, solve for x. Subtract 4, divide by 3. Next problem. Number 5. Log base 3 of x plus log base 3 of x plus 4 equals 3. I have 2 logs being added equals a number. I'm going to put the 2 logs together using property 6. That means I'm going to multiply those 2. I get a single log. It'll be x squared plus 4x. That equals 3. Now I do my loop. 3 to the 3 must be this. That's 3 to the 3. 3 raised to the 3, not 3 times 3. So 3 raised to the 3 must be x squared plus 4x. 3 to the 3 is 27, must be x squared plus 4x. And that is a quadratic equation. I move everything to one side. And then at this point, you can either use AC method or synthetic, and I don't think either one of those work because the only factors of 27 are 9 and 3. So you'll have to use quadratic formula on this. Dot, dot, dot. I can provide what the answers are later, but at least that gets you to the main part of this. The sixth one, the difference between 6 and 5 is that you have subtraction. And we know from property 7 that subtraction becomes division. And we also have a different base down, 4 instead of 3. So property 7 tells me these two will come together to become log base 4 division x over x plus 4, then equals 2. I can loop this thing around now. 4 raised to the 2 must be the inside there. So 4 raised to the 2 must be x over x plus 4. 4 squared is 16, or x times x over x plus 4. I have a rational equation. I multiply both sides by x plus 4. It'll clear out the fraction. What I do to the left, and what I do to the right, I have to do to the left. This goes away. I distribute that 16 through. I get 16x plus, what's that, 64 equals x. That linear equation can be solved. I'll do it because it's clean numbers. Subtract x from both sides, you get 15x, and then take the 64 to the other side. Then divide through by 15. So x is negative 64 over 15. You can leave it as a fraction, or you can get it as a decimal. Doesn't matter. Number 7. Log base 3x plus log base 3x plus 4 equals log base 3 of 8. I have logs on both sides. Everywhere I've got logs. So I'm going to put these two together by using property 6, which means I will multiply the x times that piece. That gives me x squared plus 4x. Then equals the other side is log base 3, 8. Now this property, I believe, was property 9, where if you have log of something equals log of something, those two somethings have to be the same. So I just take the inside here and make it equal to the inside of that one. So x squared plus 4x must equal 8. And that is a quadratic equation. I move everything to one side. And that requires probably quadratic formula again. So I would definitely be prepared for some quadratic formulas on this test. Number 8. Log base 3x minus log base 3x plus 4. Wait a minute, is that the same as number 6? It's almost the same exact problem, isn't it? Just different bases. I think I must have made a mistake when I did that. That's the same problem. So this just turns into division. I did not mean to give you the same exact type of problem twice. No harm, no foul, right? 3 to the 2 is this, so 3 squared is 9 over x times x, or x over x plus 4. And then multiply both sides by x plus 4. Since I've done this already, I'm just working it mentally here. X plus 4 here, x plus 4 here, 9 distributes, which gives us this, and then on the right side, just the x. Subtract 8, move 36 over, divide by 8. Reduce the fraction, get a decimal, doesn't matter. Leave it like that. And I'm flying through this thing. Number 9. Eight minus 3e to the 4x equals 2. This is an exponential equation, not a log equation, exponential. So to solve an exponential equation, we try and isolate the term that has the x in the exponent. So I will first subtract 8 on both sides. Subtract 8. This leaves me negative 3e to the 4x equals negative 6. I'm almost there. I'm going to divide both sides by negative 3. Divide by negative 3. Divide by negative 3. E to the 4x equals 2. Now that I have something raised to the 4x, the x is up there, I'm ready to get it out of there, but I will have to kind of reverse engineer that loop. So I know since the x is the exponent on e is the base, the 4x comes on this side, and then the 2 is here. So I can verify that e to the 4x is equal to 2, which is this. E to the 4x is 2. So that's the correct setup. I realize that log base e is natural log. So this is just natural log of 2 equals 4x. I take natural log of 2 on my calculator. I divide that by 4, and that's what x is. Anyone? 0.173? Wes? All right, number 10. Five raised to the 4x equals 2 raised to the x plus 8. Okay, problem here is that we've got x's up in the exponents on both sides of the equation with different bases. It's just a catastrophe. So what I'm going to do is I'm going to use a log right now to try and rewrite this. Now I get to choose. I can use my 5 or my 2 as my base. It'll work either way. Let me show you with the 2 since in class I did this one. I'm going to use 2 as my base. According to this equation, I have 2 raised to the x plus 8, which means this must be x plus 8. So 2 raised to the x plus 8 must equal whatever's on that side. So 5 to the 4x. Just double check it with the loop. 2 to the x plus 8, 2 to the x plus 8 must equal 5 to the 4x. 5. So that log matches that up there. Unfortunately, I still have an x trapped up in the exponent, but I can use property 8. I believe it's property 8. It says if you have a power and you have a log out there, the power can drop out in front. So I'm going to pull that 4x out front. I'll have log base 2, 5 equals x plus 8. This is just a number. Log base 2 of 5, you can do on your calculator. That's natural log of 5 divided by natural log of 2 using the change of base formula, which gives me 2.32. 2.32. So this is going to be 4x times 2.32 equals x plus 8. The last thing I'd like to do is multiply 4 times 2.32 and get 4 times 2.32. 9.28 x. So 9.28x equals x plus 8. This is a linear equation now. Just subtract x on both sides. So subtract 1x on both sides. You get 8.28x equals 8. Divide both sides by 8.28. And you have 0.966, 6, or just okay. We have a minute and a half left. Number 11. Wait, what time do we go to? We go to 4:40, don't we? Okay, never mind. We have plenty of time. We're going to finish this off. Okay, number 11. Anyone need that still? Okay. Number 11. We have, what interest rate would you need to turn 8,000 into 9,000 in 3 years if interest is compounded daily? Now I said scratch daily, right? So only do continuously. So what formula would we be using for continuously? A equals P e to the RT. I forgot to tell y'all what I call that. I call that the shampoo formula. Did anyone here use PERT plus? Don't deny it. That's some good stuff. PERT plus, you've heard of it, right? The shampoo? That's PERT. PERT. So we just need to figure out what part of this we have and what part we want to plug in. So what do we have? $8,000. We need to turn our 8,000 into 9,000, right? So 8,000 is what we're going to start with. 9,000 is what we want to end with. So how about this? A is 9,000. P is how much we start with, 8,000. E will never change, right? E is just E. Can't change what E is. R, the interest rate. Do I know the interest rate? No, it says what is the interest rate, right? That's what it wants us to find. How much time? We want to be able to do that in 3 years. So I'm going to put R times 3 or just 3R. Is that fair? Questions? We are trying to solve for R, but R is trapped in an exponent. This is an exponential equation then. Before I can sit here and try and rewrite it as a loop, I need to get rid of the 8,000 in front. So I will divide both sides by 8,000. So what's 9,000 divided by 8,000? Now can I do the loop? Okay, so when I rewrite the loop, what's the base of this log? It's going to be E. What's on this side over here on the right? 3R, and then on the inside of the log, 1.125. But what is log base E? Natural log. So we have natural log of 1.125 equals 3R. To figure out what natural log of 1.125 is, divide that by 3. And you got your answer. Wait, what did you get? 0.03926, yes. I got the same thing. So after you do that entire computation, 0.03926 is R. So that is correct. I wouldn't take off on the test for that answer, but what is that as an interest rate? Like if you were to tell someone, yeah, my interest rate is 3.9, because you would move it back to get it to a percentage, so it would be approximately 3.93 or 2, whatever, 3.93% is your interest rate. You might be able to find an interest rate at 3.93, maybe. All right, number 12. How long would it take to double your investment? Let's do triple, because I did double in class. Can we do triple? How long would it take to triple your investment if you put money into a simple interest account at 3.75% and interest was compounded, first of all, monthly and then continuously? So let's do the monthly problem first. Number 12, part I, monthly. Since interest is compounded monthly, what formula am I using? That first one, right? Not the shampoo, right? It's this one. That's our formula? Let's talk, I would put that on my cheat sheet, wouldn't you? Okay. Do you know what P is in the problem? Do you know how much we're supposed to put in? No, we just know we have to triple it, right? So P is going to be whatever we put in. Do you know the interest rate? $3.75. So 0.0375 is your interest rate. Do you know N? The number of times it's compounded? 12, because it's monthly, right? 12 monthly. Do you know what T is? No, but that's what we want, right? How long is it going to take to triple our money? So T is what we're going to try and find. Do you know what A is? 3P, good. That's the kind of big part of the problem. We want to triple our money. A is 3 times what we put in. So that's everything. Let's go back into the formula, fill it all in. I'll put it right above this. A we said was 3P equals P 1 plus R, which was 0.0375 divided by N, which was 12, all raised to the N times T, which is 12 times T. We have to get on our calculators now. Oh, divide both sides by P, right?
Yeah.
That'll kill off the P's. Get on your calculator and figure out what 0.0375 divided by 12 plus 1 is. You want to give that to me? 1.003125, and we're raising that to the 12T. Agreed? The left side is still just 3 because the P canceled. Now, I've got a pretty good looking thing here. I've got something to a power. The thing I'm trying to solve for is up here. Got a number here. Rewrite this as a log now. It'll be log. The base of this log is this ugly number, 1.003125. The other side of the equation is 12T. And then in here is 3. Verify with this little loop action that it is correct. Now what? This left side, change the base formula, right? This is natural log of 3 divided by natural log of 1.003125. You're about to get sick. You see this answer. What did you get on the left side there when you did that? 352? Point something? 0.1? Okay. Equals 12T. So now divide through by 12. 29.34 is T. It's going to take roughly 30 years to triple your money at that interest rate.
It's pretty realistic.
3.75? You definitely wouldn't get that in a savings account, like if you go to a bank. That's like less than 1%, you know. Okay, now look, for number 12, part 2, it's the same exact problem, right? But the setup's slightly different. For part 2, we're continuously compounded, right? Continuously means we're just going to change our formula. Our formula is going to be the shampoo formula instead. We know what A is, right? What's A supposed to be? 3P. P here, E to the R. We know the interest rate was 0.0375. And then T is what we're trying to solve for. The P's still cancel out both sides. 3 is equal to e to the 0.0375t. Rewrite this as a log. Log base what? E, right? And then 3 goes here, and then 0.0375t goes there. Just check it with the loop, that's right. The left side's really just what? Natural log 3. So just natural log 3 equals 0.0375t. And let's just do this all at one time. 2 natural log of 3, figure out what that is. Then divide by 0.0375. Tell me what you get. 29.229. Our answer from before, right? Continuous, when we compounded it monthly, was still about 29 years, wasn't it? Slight difference in the answer. You should get the same thing on your test. You should get slight differences in the answer, but the method in which you get to those answers is different. It's using different formulas. That's it. Boy, look at that. It only took us like, what? Maybe 30 minutes? Knock that out pretty quick. You should probably only need, what, 45 minutes for the test on Thursday?
Yeah, right.
It's the exact same.